In previous video, we talked about the wonders of forces. So in this video, we continue to talk about the intermolecular forces, and we want to talk about the special case, hydrogen bonding. Hydrogen bonding happens when the hydrogen is connected to electronegative elements like fluorine, oxygen, and nitrogen. So it's written here, it says when a molecule contains hydrogen covalently bonded to a very electronegative atom, fluorine, nitrogen, or oxygen, these molecules are attracted to each other by a particularly strong type of intermolecular force called hydrogen bond. Let's talk about the hydrogen bond a little bit here. You know that the hydrogen has one electron and its electron configuration is 1s1, so there is one electron in the s orbital. If you want to show it by the Bohr model, you have a proton in the nucleus, and around that in the 1s orbital you have just one electron. When this hydrogen is bonded to the electronegative atom, like the oxygen for example in the water molecule. Okay, this is the Lewis structure of the water molecule. Let me draw another water molecule here. Okay, when a hydrogen is connected to this electronegative atom, this shared electron pulls away from the hydrogen. So these one of the electron coming from the hydrogen, another shared electron comes from the oxygen, but because the oxygen is much more electronegative than hydrogen, both of these electrons goes away from hydrogen. So if you take these electron away from hydrogen, what remains for that one? The proton remains for that. So it means around the hydrogen we almost have the proton. Okay, we have the electron here, but most of the time this electron is around or closer to the oxygen. So we say the proton or nucleus of the hydrogen becomes unshielded. That's why these electrons, lone pairs on the oxygen atom, can come close to the nucleus of the hydrogen, and some type of attraction forms between the lone pairs here and the nucleus of the hydrogen, which we call it hydrogen bonding. So the hydrogen bonding is the special case for dipole-dipole attraction. Okay, so it's a special case of this one, and that happens when the hydrogen is bonded to electronegative atoms, which we call them fluorine, oxygen, and nitrogen. And the hydrogen bonding happens between the hydrogen of one molecule and lone pair of another molecule. Okay, so we have the hydrogen bond here. For example, the water molecule, each water molecule can have four hydrogen bonds, one between this hydrogen and lone pair, between this hydrogen and lone pair of the another water molecule, between this lone pair and hydrogen of another molecule, between this lone pair and hydrogen of another molecule. So water molecule can have four hydrogen bonds. The hydrogen bond is stronger than dipole-dipole attraction, and this is the strongest bond that we can form. Let's go back to the textbook. We can see the hydrogen bond here, so it's between the hydrogen and the lone pair that you have here. The hydrogen bond forms. One of the reasons that it can forms the hydrogen bond because the hydrogen is a small molecule, so it allows these lone pair to come close to that one. Okay, so let's look at this graph. I want to explain about this graph a little bit. Okay, this is the it shows the hydrogen bonding of the elements in the different periods. So for example, in the first one, in group 13, it can form CH4, SiH4, GeH4, SnH4. So what you can say about the intermolecular attraction between these molecules? So I want to talk about the intermolecular attraction in, mm, let me change the pen, in CH4, and what was then SiGeSn, SiH4 germanium tetrahydride, SnH4. What you can say about the boiling point of these compounds? So when you look at these molecules, all of them are non-polar molecules. So for the non-polar molecules, the only force of the attraction which are available between the molecules is London dispersion force. And by increasing the size of the molecules, the strength of the London dispersion force increases. So this one, which the molecule is bigger and is more massive, has the strongest attraction between its molecules. So this one has the highest boiling point, then this one, then SiH4, and the methane has the least boiling point. So if we want to graph this trend, the trend would be like this. Okay, so we are talking about the period 2, period 3, period 4, and period 5. Okay, so the carbon is in period 2, it has least boiling point. This one, silicon, is in period 3, its boiling point is a little bit more, then germanium a little bit more, and Sn a little bit more. So what do we have here is the period, and what do we have here is boiling points. And this is the reasonable because the element in period 5 is more massive than period 4 is more massive than period 3, and period 3 is more massive than period 2. So let's talk about the next group in the periodic table. So I go here. The next group in the periodic table is group 15. So we have NH3, PH3, ASH3, SBH3. So I write them here one more time. Okay. So you have NH3, ammonia, then you have PH3, then you have ASH3, and the last one is SPH3. So all of these molecules are polar, so they have dipole-dipole attraction. This dipole-dipole attraction available between the molecules of all of these four species. At the same time, they have London dispersion forces, because the London dispersion forces are available between all type of the molecules, and the London dispersion forces depends on the size. This one is bigger, more massive, so it has greater London dispersion force. Its boiling point is more than this one. The boiling point of the ASH3 is more than PH3. So if I want to graph the trend here, okay, the SBH3 must be somewhere here, for example. So let me delete this one. Okay, and ASH3, because its London dispersion force is weaker, it must be here. Then PH3. For NH3, we expect to be less than the other. Okay, so we expect that the trend would be something like this. But when you check suddenly for NH3, the boiling point increases. So instead of being this one, the boiling point increases. So what this increase in boiling point shows you? This shows you that you have another force of attraction between the molecule in NH3 that cause its boiling point to increase, and that is hydrogen bonding, because in NH3 hydrogen is connected to electronegative atom of nitrogen, and they can form the hydrogen bond between the hydrogen and the lone pair of the nitrogen. We can see the same thing in the next group in the periodic table in H2O, H2S, H2SE, H2TE. Let's look at your book here. Okay, so here it's shown here. So here you have H2TE, then here in period 4 you have H2SE. So this one shows H2SE, this one is H2S, and for the water molecule we expect to be smaller than that one. The boiling point must be lower than that other, but suddenly the boiling point increases, and that is because of the hydrogen bond which you have here. Okay, and same thing you can see for group 17. Okay, so you have HF, HCl, HBr, and HI. Okay, so when you are going up the group, the size of the molecule becomes smaller, its London dispersion force decreases, so the boiling point decreases as well. So you can see this is the HI, this one is HBr, this one is HCl. So we expect if the only force was the van der Waals forces, the HF must be somewhere here, but suddenly it increases. This shows that we have stronger force in this case, which is hydrogen bond. And you can see in the periodic table, the hydrogen bond forms between the hydrogen and only these three elements, F, O, N. Okay, let's go back to your textbook. So this is important. So hydrogen bonding only occurs between the molecule in which the hydrogen is bonded directly to the fluorine, nitrogen, and oxygen. So maybe in one molecule you have hydrogen and you have oxygen, but the hydrogen is not connected to the oxygen. In that case, you don't have hydrogen bond. So be careful in the questions. So look at the look at this table that you have here. You have two type of the molecules. One is methoxymethane, CH3O CH3, and the other one is ethanol, CH3CH2OH. Ethanol is alcohol, methoxymethane is ether. The molar mass of both of them are equal, 46, 46. Okay, so it means both of them, the London dispersion force for both of them are almost equal. Both of them are polar molecules, so both of them they have dipole attraction. But why the boiling point of the ethanol is positive 79, but for the methoxymethane is negative 23? Okay, so this one is gas at room temperature, this one at room temperature is liquid. So this shows that you have a strong attraction between the molecules of the ethanol. That's why at room temperature the molecule remains close to each other and they are liquid, but for the methoxymethane the attraction between the molecules are small, so that's why at room temperature they are gas. And that is the hydrogen bond. In the alcohol, hydrogen is connected to the oxygen, so it can form hydrogen bond with the lone pair of the oxygen in adjacent alcohol molecule. But in the methoxymethane, although you have hydrogen and oxygen, but the hydrogen is not connected to the oxygen, so it cannot form the hydrogen bonding. Okay, so the figure 417 shows the hydrogen bonding which are available between the water molecule. Each water molecule can form four hydrogen bonds with the neighboring molecules. Okay, it says liquid water contain fewer than this number, but in the solid form, ice, each H2O is maximally hydrogen bonded in this way. So it can have up to four hydrogen bond, but in the liquid It may be one or two, but when the water solidifies and converts to the ice, it can form up to four hydrogen bonds. And for forming four hydrogen bonds, water molecules must go a little bit away from each other to have appropriate orientation for forming four hydrogen bonds. So when the water molecule goes a little bit away from each other, its density decreases. So most of the molecules in the solid form are more packed and more dense than the liquid. But for the water and the ice, the situation is inverse of this one, because when it wants to form the ice, it wants to form four hydrogen bonding, and for doing that, the water molecule a little bit go away from each other, and the solid or ice become less dense than the water. That's why the ice, which is less dense than the water, floats on the ice. As you can see here in these big iceberg, the iceberg is less dense than the water. So that one, it floats on the surface of the water. Okay, because it has four hydrogen bond, and for forming four hydrogen bond, the water molecule must go a little bit away from each other. Okay, so it's explained here. Says the result is the tetrahedral arrangement that holds the molecules a fixed distance apart, forming fairly open structure, which is actually less dense than the liquid. It talks about the ice. Okay. This is a remarkable fact. In nearly all other substances, solid form are closer packed, so they are more dense. But in the water and ice, the ice is less dense. Okay, let's go to the next page. So in the next page says you cannot have only okay, you don't only have the hydrogen bond between one molecule and another molecule. When you have a very large molecules, you can have hydrogen bonding within the molecules. The famous example is the DNA. DNA is composed of the very long chain of the molecules. So you have two long chain in the DNA. These two chain are connected to each other by their hydrogen bonding. Okay, you can see here in this picture this type of the hydrogen bonding. So this is one molecule of the DNA that you can see here. This is one molecule of the DNA, or one strand of that one, and this one is the second strand of the DNA. And you can see in the strand which you have at the left side, hydrogen is connected to the nitrogen. So this hydrogen can form the hydrogen bond with the lone pair of the oxygen here. So you have the hydrogen bond between these two strands of the DNA. So this is only one molecule. You have hydrogen bond within the molecule. You have the almost similar situation for the proteins. The proteins are very large molecules, and sometimes on one part of the molecule oxygen is connected to the hydrogen, and on the other side of the molecule you have lone pair on the hydrogen, and there can be hydrogen bond between these two groups. So this is the hydrogen within the molecule. Okay, so look at this table. This table summarizes all of the intermolecular forces that we have talked about it in these two videos. The first intermolecular forces is the London dispersion forces. It available between the non-polar molecule, between the polar molecule, and even between the molecule which contains HO, HN, and HF bonds. The next one is dipole-dipole attraction. Dipole-dipole attraction is not available between the non-polar molecules. It's only for the polar molecules, include the molecules which the hydrogen is connected to the found elements. And the strongest one is hydrogen bonding, which is only available between the molecules which hydrogen is connected to found elements. So from the top to the bottom, the strength of the intermolecular force are increasing. Okay, so we finish this video here. In the next video, we discuss about the properties of the covalent compounds, properties of the molecules based on their intermolecular forces. And the most important properties that we want to discuss is the melting point and the boiling point of the molecular compounds, and later on, we talk about the solubility of the molecular compounds and the different material in each other.